Most people step over rocks that shimmer faintly in the right light, unaware they might be standing atop a mineralized vein. The texture of surface rocks, especially those with subtle banding, irregular fracturing, or a greasy luster, can silently indicate the presence of gold, silver, or gemstones below. The first signs are rarely flashy. They're overlooked precisely because they mimic the ordinary. One key feature to watch for is a vuggy quartz outcrop, a rough, porous-looking mass where quartz has filled spaces in host rock but left small cavities, often lined with tiny crystals. These aren't just pretty geologic leftovers. Vugs can form during hydrothermal processes, which are the same processes responsible for depositing metals and precious stones into surrounding fractures. A casual hiker might see crumbling white rock. A trained observer sees a frozen record of fluid flow that likely carried minerals of interest. Equally telling are rocks with a distinct iron oxide stain, shades of red, yellow, or brown, often coating quartz or altered host rock. These are known as gossans, and while the visible iron content is usually worthless, it forms when sulfide minerals oxidize at the surface. Since sulfides often host gold, the gossan becomes a trailhead pointing deeper. It doesn't guarantee value, but it rules in further investigation. Beyond color and texture, pay close attention to fracture density and orientation. A quartz-filled vein cross-cutting a foliated metamorphic rock may hint at tectonic activity that open pathways for mineral-rich fluids. Vein width matters too. Generally, veins less than 2 cm wide are unlikely to be economic unless heavily mineralized. But even narrow veins can be critical if they connect to larger systems or occur in swarms. In some cases, the presence of epidote, chlorite, or sericite, minerals that often form from hydrothermal alteration, can elevate an otherwise plain outcrop into a serious exploration target. These alteration halos can extend tens of meters beyond a vein, creating a broader footprint than the vein itself. Field confirmation often starts with basic tools: a loop for close inspection, a magnet to test for associated magnetite or pyrrhotite, and a quick hardness test on any exposed crystals or vein material. Quartz at Mohs 7 won't scratch with a knife blade, but anything significantly softer, like weathered carbonate, should be tested cautiously. Heft can also reveal something unexpected. Dense rocks near 5G/cm3 may carry barite or metallic sulfides, not just silica. As this pattern of minor surface clues begins to align, the next question arises. How do we distinguish between rocks that simply look mineralized and those that truly carry value? That's where visual hints give way to structural logic. A rock's surface appearance often lies. Smooth, weathered blocks can conceal dense mineral concentrations, while flashy-looking quartz might be nothing more than dead silica. What separates an ordinary rock from a potentially valuable one is rarely obvious at first glance, but the difference becomes clear with a simple sequence of tactile and optical tests. First is luster, the way a rock reflects light. Quartz commonly shows a vitreous glassy luster, while minerals like serpentine or jadeite often appear waxy or greasy. A metallic sheen may signal sulfide presence, pyrite, chalcopyrite, galena, but needs follow-up since fool's gold has tricked even trained eyes. A key test is fracture. True metallics will cleave or break differently than glittering micas or silica. Next comes weight in hand. This field intuition improves with time, but dense rocks, especially those with embedded sulfides, feel heavier than they should. Barite, hematite, galena, and even native metals increase specific gravity significantly. A rock the size of a fist that strains the wrist could be a keeper. Typical quartz or granite hovers around 2.6 G/cm3. Anything in the 4+ range deserves specific gravity testing via water displacement. Translucency also matters. Holding a chip against the sun, nephrite jade will often glow deep green around its edges, whereas serpentine tends to stay opaque. Similarly, precious opal may show internal color flashes under strong light, while common opal, still hydrated silica, remains dull. In the field, this test doesn't prove value, but narrows the candidate list. Fracture and cleavage offer another diagnostic axis. Quartz fractures conchoidally in smooth, curved surfaces. Feldspar may cleave in flat, blocky plains. Garnet often fractures unevenly but resists scratching. If a stone breaks with jagged edges and doesn't respond to steel tools, it could be corundum or another ultra-hard mineral, worth testing further with silicon carbide sandpaper or a scratch plate. Some rocks also show unusual behavior when exposed to temperature changes or UV light. Under long-wave UV, scheelite fluoresces blue-white. Some diamonds fluoresce blue. Calcite may glow red or orange. While not diagnostic alone, these reactions can confirm a working theory when paired with known indicators. Finally, magnetism is underused but powerful. A cheap magnet can detect magnetite instantly, but also ilmenite, a common kimberlite indicator. Weak attraction may signal pyrrhotite or chromite. In contrast, non-magnetic but heavy grains could mean gold, galena, or cassiterite. A basic field sweep, especially on concentrates or vein material, saves hours of lab work. Each of these tests filters down the overwhelming abundance of interesting rocks to a manageable set of candidates. But rocks don't just signal what they are, they also tell you where to go next. Certain structures concentrate value predictably, and once you know how to read the folds and faults, a whole new layer of clues unfolds. Gold and gemstone deposition doesn't occur randomly. It follows pressure, temperature, and structural geometry. One of the most consistent indicators of hidden mineralization is the presence of folded or fractured rock formations that have acted as natural traps for hydrothermal fluids. These folds, faults, and shear zones become highways and holding tanks for valuable material deep underground. The first type to recognize are anticlines and synclines. In an anticline, rock layers arch upward. In a syncline, they dip downward. These bends don't just deform the landscape, they redirect subsurface fluid flow. In areas where compressive forces have folded bedrock, fluids tend to migrate along the fold hinges and limbs, especially where brittle rocks like quartzite or shale intersect with more ductile units. Gold often accumulates along anticline crests where fractures open upward and pressure drops sharply, causing minerals to precipitate. Equally valuable are fault intersections. A single fault might bleed fluid, but when two faults intersect, especially at different angles or rock types, they can form high-permeability zones where fluids mix, cool, and deposit load. These structural junctions often host quartz sulfide veins, with mineralization most intense where deformation was greatest. Some of the world's richest lode gold deposits occur at these fault junctions. In the field, look for drag folds, slickened sides, polished fault surfaces, and abrupt rock type changes. These suggest a dynamic zone with past fluid movement. On weathered surfaces, iron-stained shear zones or quartz stringers often trace the geometry of deformation. Even small-scale folding, visible in road cuts or riverbanks, can guide larger exploration patterns if it reflects regional stress fields. Another vital feature is the contact zone, where two different rock types meet. Especially when hard, brittle units like granite meet softer, reactive units like limestone or ultramafic rock, there's potential for replacement-style mineralization. Carbonate rocks, when exposed to acidic hydrothermal fluids, can dissolve and redeposit metals in situ. Skarns, which often form this way, may contain tungsten, garnet, epidote, or even gold. A practical example: if you find a limonite-streaked quartz vein cutting across a folded slate unit, and there's nearby contact with mafic or ultramafic rock, you've stumbled into a structurally complex zone with multiple fluid pathways. This is not just a geological curiosity, it's a grid-worthy location. Terrain clues extend to the surface as well. Streambeds that bend sharply or bedrock that shows offset joints or veining may reflect deeper structural controls. Even boulder trains, scattered angular blocks aligned downslope, can trace the erosion of a mineralized structure. But folds and fractures don't just localize gold. They also control where specific gemstones form. Tourmaline, for example, often grows in pegmatite veins emplaced along tension cracks. Nephrite jade forms in shear zones where serpentinite has been compressed and hydrated. These structural features dictate not just the location, but the texture and quality of the minerals they host. Still, not all promising formations pay off. Some carry only relics of fluid flow, long since exhausted. The challenge then is to pair structure with chemistry. The next signal to look for is a unique family of rocks that doesn't just deform, it transforms under heat and pressure, leaving behind unmistakable signs of deep-sourced mineral systems. In regions where ultramafic rocks surface, there's often more beneath the green-black sheen than meets the eye. Serpentinized formations, originally mantle-derived peridotite and pyroxenite altered by water, frequently contain trace indicators of far rarer materials: jade, chromite, and even accessory diamonds. Yet these same rocks are regularly dismissed as worthless by casual prospectors unfamiliar with their implications. The process begins deep within subduction zones or ancient suture belts, where oceanic crust was forced beneath continental plates. As these ultramafic rocks rose through faults or tectonic windows, they reacted with circulating hydrothermal fluids. This hydration transformed olivine and pyroxene into serpentine minerals, often visible on the surface as smooth, greenish-black outcrops with a waxy or fibrous luster. Their appearance is distinct, yet easy to overlook without knowing what they signify. Nephrite jade, a tough interlocking variety of actinolite and tremolite, almost always forms in these serpentinized zones. Its presence depends not just on chemistry, but also on structural setting, where shear zones concentrate stress and fluid flow. Often, nephrite occurs as veins or lens-shaped pods along fault lines, enclosed in massive serpentinite. The surrounding rocks, chlorite schists, talc carbonate seams, or epidote-rich veins, can act as a fingerprint for jadogenic environments. One diagnostic clue is asbestos-like veining, thin, fibrous seams of tremolite or chrysotile that cut across the host rock. While these can be hazardous if disturbed, their visual presence underlines a specific pressure-temperature regime in which jade may have also formed. Another is the density test. Nephrite runs about 2,930 G/cm3, heavier than serpentine 2,6, but lighter than jadeite 3,335. In the field, heft helps, but a water displacement test refines your estimate. Chromite is another high-density mineral often found in these rocks, appearing as black, granular seams or nodules. A strong magnet sweep can identify magnetite first, but chromite is weakly magnetic, meaning it may resist even a neodymium magnet. When crushed and panned, chromite concentrates as dark, shiny, angular grains that feel surprisingly heavy. Its presence can signal layered mafic intrusions or altered ophiolite belts, both potential hosts for platinum group elements or diamonds if the conditions align. And then diamonds. While commercial-grade diamonds require very specific host rocks, kimberlite or lamprey pipes, it's not impossible to find accessory microdiamonds or their indicators in serpentinite belts. Pyrope garnets, chromite, ilmenite, and spinel may drift into altered zones during tectonic mixing. These don't guarantee diamond presence, but they do raise the geological stakes, especially if accompanied by high-pressure minerals like coesite or glaucophane. In practical terms, serpentinized zones are easiest to identify on maps by searching for ultramafic units, ophiolites, or tectonic melange. On the ground, their low weathering resistance often leaves smooth, rounded outcrops or crumbly greenish soil. Some serpentinite bodies even produce a distinct slick-inside polish, smooth surfaces that feel greasy to the touch. Yet for all their promise, serpentinite-hosted zones require caution. Steep slopes, loose regolith, and potential for asbestos exposure make fieldwork here more technical. Local laws may also restrict collecting or trenching in these sensitive areas, especially if culturally significant jade is present. Still, when these rocks appear in the right structural context, shear zones, tectonic contacts, or folded belts, they become more than exotic geology. They mark access corridors to some of the rarest mineral systems on Earth. The question is, how do you trace that potential across surface expressions? That's where gossans, those rusty weathered zones, come sharply into focus. Rust-colored rock outcrops are often written off as stained or weathered, but in mineralized terrains, that oxidation might be a vital surface clue. Gossans' iron-rich, oxidized zones formed from the weathering of sulfide minerals serve as natural signposts for underlying gold, silver, and base metal systems. Despite lacking visible gold, they've historically led to some of the world's richest discoveries when understood in context. A classic gossan forms when sulfide-bearing rock, containing minerals like pyrite, chalcopyrite, or galena, interacts with oxygen and water near the surface. These reactions strip away soluble elements, leaving behind iron oxides like limonite, goethite, and hematite. What remains is often a crumbly, reddish-brown caprock, light in color, but heavy with implication. In the field, these gossan caps stand out by color and texture. Limonite streaks easily to a yellow-brown powder and feels earthy to the touch. Goethite can appear more fibrous or botryoidal grape-like and may stain red-brown. Hematite tends toward a darker, metallic red and shows a strong red streak. None of these iron oxides are valuable in themselves, but their position and composition reveal what may lie beneath. The key is association. If gossan zones are found cutting through or aligned with quartz veins, shear zones, or altered felsic volcanics, they're far more than surface rust. They're vent scars of an ancient mineral system. In gold systems, especially in greenstone belts, gossans often cap pyritic zones where gold was deposited along with sulfides. Though gold resists oxidation and doesn't travel far, it can still remain locked in residual clays or limonite, invisible without assay. One simple test: pan material directly from a gossan zone. Even if native gold isn't visible, you may retrieve heavy grains, magnetite, hematite, or even tiny specks of sulfide remnant. A magnet can isolate magnetic components, while acid tests, carefully applied in the field, may reveal carbonate alteration or hidden sulfide relics beneath oxide coatings. In some polymetallic systems, gossans also indicate zoned alteration halos, broad regions where hydrothermal fluids altered the host rock chemically. These halos can host not only gold but also silver, zinc, and copper. Observing changes in rock color, clay content, and texture around the gossan can help delineate these halos. For example, a gossan surrounded by kaolinitic clay alteration may mark the upper parts of a one-spoiling fluid system. A valuable variant is the silicified gossan, where quartz and iron oxides have hardened the cap, forming a tough, rusty outcrop resistant to erosion. These gossans are more durable and often directly overlie feeder zones. Though their hardness can make trenching difficult, the effort pays off when samples from depth confirm sulfide remnants or elevated trace elements. However, not all gossans are created equal. Some form over barren pyrite zones, offering color without content. Others may be misleadingly rich in iron due to later weathering processes, not orogenesis. That's where geochemical assays or portable XRF can offer early discrimination, testing for elevated gold, arsenic, or pathfinder elements like antimony and tellurium. Where granite intrusions meet the surrounding country rock, the chemistry and pressure-temperature conditions can shift drastically, creating ideal traps for rare minerals. These contact zones, often riddled with fractures and veins, are the crucibles where tourmaline, garnet, beryl, and other gemstones crystallize in pegmatitic pulses. But the visible boundary isn't always sharp, and missing it means walking past the source of high-grade specimen material. Pegmatites, extremely coarse-grained igneous rocks, often form as the last fraction of a granitic melt, enriched in volatile elements like boron, fluorine, and lithium. These pockets cool slowly, allowing large, well-formed crystals to develop. When this late-stage magma injects into fractures or between bedding planes at the granite contact, it creates veins or dikes lined with gem minerals. The shape, orientation, and mineral zoning of these pegmatites often track with the geometry of the host rock and the stress regime during emplacement. Tourmaline is one of the most diagnostic species in these systems, especially in lithium-rich pegmatites. It forms as elongated, often striated crystals in black schorl, green, pink, or even blue hues. A handheld magnet may detect iron-rich varieties faintly, but color zoning and transparency become the primary field clues. At the contact zone, tourmaline may appear first as radial sprays or scattered grains, becoming denser toward the core of the vein. Beryl, the mineral family that includes aquamarine and emerald, is another hallmark of these zones. In its raw form, beryl often presents as pale green or blue hexagonal prisms with a greasy to vitreous luster. Hardness is near 7.58, and it resists steel blade scratches easily. Its presence typically coincides with high alumina feldspars and muscovite or lepidolite mica, another tip-off that a volatile-rich pegmatite is nearby. In beryllium-bearing zones, even imperfect or cloudy beryl can signal a vein worth opening. Garnet, while more widespread, also concentrates in these settings, particularly almandine and spessartine varieties. In pegmatites, garnets are often large, euhedral, and deeply colored. A field knife won't scratch them, hardness 6.57.5, and they often show a dodecahedral habit. Their density and refractive index make even small fragments sparkle unusually under bright light, another easy test with a loupe. The real challenge is distinguishing barren pegmatites from gem-bearing ones. Barren types often lack accessory minerals, appearing as a coarse mix of quartz and feldspar with no obvious zoning. Productive pegmatites show vertical or horizontal zoning, tourmaline and garnet near the walls, beryl or spodumene toward the center. A rock hammer and careful sectioning across exposed veins can reveal this internal architecture. Mapping the granite contact itself can be done with compass and altimeter. Look for changes in mineralogy, especially the transition from biotite-rich granite to hornfelsed or metasomatized country rock. Skarn minerals, garnet, vesuvianite, epidote, may appear where carbonates meet the intrusion, signaling past fluid rock interaction. These boundaries, particularly where fractured or faulted, deserve tight gritting and sampling. Water-worn boulders downstream from granite contacts can also carry evidence. Pegmatitic float with visible tourmaline or mica suggests upstream veins, even if outcrops are buried. Panning below these sites can yield mica flakes or heavy garnet grains as further confirmation. Quartz veins are everywhere, running through mountain faces, road cuts, creeks, but only a minority hold economic value. To the untrained eye, they all look promising. Yet certain physical and contextual clues can help prioritize which veins to test first and which are likely barren relics. The key lies in reading not just the quartz, but its mineral companions, structure, and geological relationships. Start with vein thickness and continuity. Thin stringers less than 2 cm can indicate a mineralizing system, but they rarely carry significant concentrations unless tightly spaced or clustered in a swarm. Productive veins tend to be thicker, 5 cm or more, and show clear directional extension, often traceable for meters or even kilometers. A wide, consistent vein with mineral inclusions warrants immediate attention, especially if it crosscuts older structures. Then consider crosscutting relationships. A quartz vein that intrudes across folded bedding or earlier deformation zones is younger and possibly mineralizing. In contrast, veins that parallel layering may be syngenetic and barren. Look for veins that offset, displace, or inject along multiple orientations, especially near fault zones. These cross-cutting features often hosted fluid pathways during peak mineralization events. Texture matters too. Massive, milky quartz with no inclusions tends to be low interest, but vuggy quartz, marked by cavities lined with crystals, or quartz containing iron oxides, sulfides, or banded silica suggests past hydrothermal fluid action. Even small veins with visible pyrite, chalcopyrite, galena, or sphalerite should be flagged. In low sulfidation systems, fine-grained gray quartz with subtle crustiform or coliform banding can indicate precious metal deposition phases. One fast field test is to chip samples along the vein at regular intervals, then pan or crush small amounts to check for visible metal or heavy mineral residues. A hand lens may reveal fine sulfide dissemination, metallic specks, or secondary oxidation zones. Rusty weathering along the vein wall, especially in red or orange hues, can signal oxidized pyrite, a gold companion. In some terrains, Quartz may be accompanied by telltale alteration halos. Cerussite, a silky white mica, chlorite, soft green mica, and kaolinite, chalky white clay, often surround productive quartz veins. These minerals signal that acidic fluids altered the host rock, a common precursor to precious metal deposition. Even without visible metal, the presence of alteration minerals supports further testing. Structural context deepens the evaluation. Veins located at dilational jogs in fault systems, areas where the fault bends or splays, often become high-volume fluid conduits. These can form ore chutes, localized enrichments that may run vertically for tens of meters. If a vein thickens or changes mineralogy suddenly, it could mark one of these high-grade pockets. Still, danger lies in assuming all sulfide-bearing quartz is rich. Arsenopyrite, pyrrhotite, and even marcasite can look similar to gold-bearing pyrite, but without meaningful metal content. That's where field tools make the difference. A magnet may isolate pyrrhotite. A quick acid test, using HCl, can help distinguish carbonate versus sulfide alteration. And UV light may hint at scheelite or fluorite presence, both potential companions in tungsten or silver systems. Greenstone belts are legendary in mining history, hosting major gold districts from Canada to West Africa. But they're also geological tricksters. These ancient volcanic sedimentary terrains, often 2.5 to 3.5 billion years old, can lure prospectors with promising textures and mineral traces, only to deliver barren rock. The challenge is distinguishing productive zones from their lookalike neighbors, a task that begins with structural awareness and ends with the right tests. Greenstones are typically made of metabasalts, tuffs, banded iron formations, and ultramafic flows, rocks formed in early oceanic crust and later deformed and metamorphosed. These sequences are often tightly folded, faulted, and intruded by late-stage granitic bodies, creating perfect conditions for hydrothermal systems. Gold is usually hosted in quartz veins, shear zones, or pyritic replacement zones, but not all veins are equal, and not all pyrite is gold-bearing. The most common pitfall is assuming that any pyrite-rich zone indicates gold. In greenstone contexts, pyrite without arsenopyrite or no cerussitic alteration often signifies barren zones. Productive systems frequently show multiphase quartz veining, pervasive carbonate or cerussite alteration, and trace arsenic. The real signal isn't the pyrite, it's the fluid history recorded in the surrounding rock. One strategy is to examine vein density and orientation. Productive quartz veins often appear in swarm patterns or N-echelon arrays, cutting across schistose or foliated host rock. If these veins display visible deformation, boudinage, pinched segments, folding, or cross-fiber mineral growth, they likely formed during active tectonics, a key condition for mineralizing fluids to circulate and concentrate metals. Alteration halos provide the second filter. Productive zones often show a softening of the host rock due to cerussite, chlorite, or carbonate overprint. A subtle change in hardness, color from green to pale beige or white, or texture may indicate that the rock has been leached, replaced, or recrystallized by hydrothermal fluids. Even without visible gold, this alteration is often the best predictor of a productive system. In terms of accessory minerals, look for arsenopyrite silvery metallic, striated hard, tourmaline black needle-like inclusions in quartz, or anchorite brownish carbonate veins. Their presence often correlates with elevated gold in known camps. Crushing samples from such zones and panning the finds may reveal fine gold, even if invisible in hand specimen. Still, false positives are common. Mariposite, a green chromium mica often found in altered ultramafic rocks, is beautiful and misleading. Its presence means hydrothermal alteration occurred, but it doesn't confirm gold. Similarly, banded iron formations may carry pyrite and magnetite but lack economic metal content. Magnetic susceptibility and conductivity tools can help separate signal from noise, but the ultimate filter is geochemical analysis or repeatable field sampling. One unique test for greenstone terrains is selective pan concentration. When done downstream of a quartz-veined, altered belt, a heavy mineral trap can accumulate tiny garnets, ilmenite, magnetite, and possibly free gold. Mapping these trap sites across a fan or bench system helps trace source direction. If several traps yield fine gold consistently, it's likely not an anomaly, It looked like a dud, no visible gold, no sulfides, not even iron staining. Just a pale, fine-grained rock on a ridge shoulder, part of an altered greenstone package. But when a conductivity meter was swept across its surface, the needle twitched. The rock wasn't dead, it was charged. That single anomaly reframed the entire section, proving how hidden mineralization can hide beneath bland surfaces, only detectable through electrical response. This is the power of induced polarization, IP, and electromagnetic M tools. While visual tests target surface traits, geophysical tools respond to how rocks conduct or store electrical charge, properties often linked to disseminated sulfides or conductive graphite, even if those minerals aren't visible. In many gold systems, especially in greenstone belts and altered volcanics, gold occurs not in bright veins, but disseminated in microscopic sulfide grains, pyrite, arsenopyrite, or chalcopyrite, dispersed through the host rock. The handheld electromagnetic reader flagged the sample with low resistivity, suggesting it could conduct current more than surrounding rocks. That alone didn't confirm mineralization. Graphite, clay, or even waterlogged zones can trigger similar responses. But this rock wasn't wet, wasn't layered graphite, and its alteration halo matched known hydrothermal footprints. Weak sericite overprint, trace carbonate veining, and faint silvery glints under a loupe. The next step was to run a thermal conductivity test, a method borrowed from diamond testing. Diamonds transmit heat almost instantly, while most minerals, including quartz and feldspar, act as insulators. While this isn't diagnostic for gold, it can help separate high-conductivity materials like native metals or sulfides. The test confirmed slightly elevated conductivity, enough to warrant a sample cut and crush. Crushing revealed another clue. The fresh interior of the rock showed fine-grained sulfide dissemination, pyrite and arsenopyrite in a matrix too tight to spot in the field. A streak test showed a faint black smear. Acid application fizzled slightly, indicating minor carbonate presence. Panning the crush yielded heavies, but no visible gold. Still, the presence of sulfides, low resistivity, and known greenstone context stacked the evidence. The critical takeaway is this: conductivity anomalies often precede visible ore. Sulfide grains, especially when finely disseminated, may not register to the eye or hand lens, but under electrical scrutiny they light up, offering the first data point in a blind system. These rocks are often dismissed as unmineralized, despite hosting some of the most consistent, albeit lower-grade, gold deposits. One key is to map conductivity in conjunction with structure. Zones of shearing, fold thickening, or fault intersection that also register electromagnetic anomalies deserve priority. Especially in terrains where oxidation has stripped away visual markers, these hidden, hot rocks can signal blind deposits, mineralization sitting below barren caprock or weathered surface layers. Of course, conductivity alone isn't a green light. Carbon-rich sediments or clay-filled shear zones can mislead. But paired with alteration, structural context, and subtle density or luster cues, it becomes a powerful predictor. And sometimes these hot rocks point not to lodes, but to where gold has moved over time, settling in ancient flows now buried under today's terrain. That's where the next frontier lies, reading the old river systems. Gold doesn't stay where it falls. Over millennia, erosion and water flow break down bedrock, liberating gold particles and transporting them downstream, only to deposit them again in predictable patterns. The key to finding this placer gold isn't modern riverbeds, but ancient ones, those now buried, shifted, or elevated above today's flow. These paleo-channels and high benches often hold richer concentrations than active streams, and reading their geometry is a skill few master. A productive placer setting forms where water velocity suddenly drops, causing heavy materials like gold to settle out. This typically happens in inside bends of meanders, where flow spirals slow, or behind obstructions like bedrock knobs, log jams, or boulder clusters. But these active zones are often worked out or overregulated. The deeper opportunity lies in abandoned channels, where rivers once flowed but have since migrated. Look for high benches, flat terraces that sit above the current river level, sometimes tens of meters up. These benches often preserve gravel sequences from former riverbeds, including false bottoms of hardpan or clay where gold concentrates. Digging test pits through these benches can reveal stratified layers, light sands above, coarse gravels below, and black sands or clay just above bedrock. It's here that the heaviest material, including coarse gold, typically rests. But paleochannels aren't always visible from the surface. In dry gulches or desert washes, the channel may lie beneath colluvium or alluvium, masked by vegetation or slope wash. Here, aerial imagery, LiDAR, or even topographic maps can help. Tracing sinuous depressions, relict meanders, or subtle slope changes across terrain often reveals the buried path of an ancient stream. An even richer target is a buried confluence, where two paleochannels meet. These junctions concentrate hydraulic energy, and when flow subsides, gold drops out in thick lenses. Test pitting across these confluences, even at shallow depths, can recover coarse flakes or nuggets that haven't moved in centuries. The best signs include water-worn quartz, black sands, magnetite, and occasional garnet grains, all dense, transported together. Tools matter here. A 20 sieve ~0, 85 lets you isolate fines. A 40 sieve ~0, 425 captures even smaller gold. Using a batte or traditional pan, watch for material that settles last, flat, bright, and inert. Magnetite and ilmenite sweep out early with a hand magnet, letting you focus on what remains. Gold typically shows a buttery yellow tone, doesn't float, and moves sluggishly in water. Flour gold, tiny flakes, tends to smear in the pan but stays separate from mica or pyrite when rocked properly. False positives abound. Mica flakes sparkle and float, but they're light and often shift erratically. Iron pyrite is brittle, breaks under pressure, and often oxidizes to a dull hue. Lead shot from hunting or fishing gear is common in old streams, but it deforms easily under pressure, unlike gold. Finally, not all placers are erosional. In volcanic regions, gold may concentrate in alluvial zones, where weathering breaks rock in place, and gold accumulates without significant transport. These settings often occur just downslope from quartz veins or mineralized shear zones, creating pocket placers that mimic stream behavior. The key is recognizing that surface clues, odd boulders, high terraces, ancient gravels, often sit atop deep value. But the biggest reversal comes when a once promising system yields nothing and forces a reevaluation of where the real deposit lies. That moment comes when a seemingly barren vein leads to an unexpected host. It had all the hallmarks: a robust quartz vein, rust-streaked flanks, coarse-grained texture, and even trace sulfides. The early field tests looked promising: moderate density, weak magnetism, faint sericitic alteration. Samples were collected, crushed, panned. But after weeks of mapping and anticipation, the assays came back: gold under detection limit. The vein, despite its textural perfection, was barren. The setback forced a crucial shift from chasing quartz to studying its surroundings. False positives like this are common in fieldwork, especially when quartz is treated as the prize rather than the pathway. In many systems, gold isn't hosted in the quartz itself, but in the altered wall rock or at contact zones where fluids reacted with the surrounding lithology. In this case, follow-up analysis of the argillized metavolcanic host, once dismissed as background, revealed elevated arsenic and trace gold, missed in the initial focus on the vein. This reversal highlights the importance of fluid-rock interaction zones. When hydrothermal fluids rise, they often carry gold in solution. Quartz precipitates early as pressure drops, but gold doesn't necessarily follow. Instead, it bonds with sulfur in solution and precipitates when pH, temperature, or redox conditions shift, often outside the vein, in porous or reactive wall rock. Sericite, chlorite, and carbonate halos mark these reaction fronts, Ignoring them means ignoring the true target. In this case, microscopic arsenopyrite dissemination was only visible in polished section. But the key field clue had been there all along, a narrow selvage of bleached, softened rock flanking the vein, only slightly different in hue and texture. Portable XRF testing later confirmed elevated AS and SB, pathfinder elements closely associated with orogenic and Carlin-style gold systems. When tested in grid fashion upslope and downslope, several of these altered zones showed increasing signal. A second error had been in vein orientation. While the main quartz body trended east-west, minor cross veins on a north-south trend cut through foliation and showed tighter sulfide stringers. Sampling these yielded better results, not high-grade, but above background and consistent. This pointed to a structural control missed initially, a late-stage reactivation fault, not the primary vein, as the main fluid conduit. The lesson was clear: quartz without context is meaningless. True mineralization is a product of three variables: structure, chemistry, and timing. Without all three aligning, a vein is just decoration. But when the surrounding rock is receptive, when fractures create pathways, chemistry enables deposition, and fluid pressure sustains flow, then even subtle alteration zones can be the main event. This strategic pivot refocused the mapping effort. New attention was given to foliation parallel shears, oxidized carbonate zones, and subtle breccia textures in volcaniclastics. What had seemed like background noise turned out to be the signal, especially once geophysical data was layered over the new structural model. As the picture sharpened, another question emerged. How reliable is this new approach beyond one site? That's where outside validation and known methodologies become vital, bringing in published models, institutional knowledge, and large-scale mapping to anchor the emerging theory in proven ground. For all the visual clues and field tests, nothing rivals the predictive power of indicator minerals, tiny grains that act as geological breadcrumbs pointing toward hidden mineral systems. Among them, chromite, ilmenite, and garnet are among the most telling. Their presence can confirm proximity to deep-sourced pipes, lamproitic systems, or even old weathered deposits now buried beneath later cover. But these indicators are only useful when properly identified, separated, and interpreted. Begin with chromite. This dense black mineral often appears granular and submetallic, sometimes with a faint bronze sheen. In the field, it's hard, often slightly magnetic, and typically found in ultramafic or mafic rocks, or more critically, in the weathered soils derived from them. When recovered from heavy concentrates, chromite grains stand out by weight and luster. They resist deformation and under a hand lens often appear rounded or pitted from transport. Their presence, especially with garnet and ilmenite, raises the probability that you're within range of a kimberlitic or lamproitic source body. Ilmenite, while similar in color, behaves differently. It tends to have a slightly more metallic luster and is weakly magnetic. A key trick in the field is the magnet sweep. Magnetite will leap to the magnet, but ilmenite will respond only faintly, if at all. Under reflected light, ilmenite often shows internal reflections and subhedral crystal faces. It's a common companion in both diamondiferous and RE-rich systems. Garnet is more varied and more complex, but also more informative. In heavy mineral concentrates, garnets typically appear as rounded, pink, red, or brown grains, often translucent. Their shape and color can hint at their origin. For example, pyrope garnet, a high magnesium type, is a key indicator of diamond-bearing kimberlite. These garnets are deep red to purple and unusually dense. Even without lab analysis, they feel heavy and smooth, and may fluoresce under shortwave UV depending on composition. In practice, you'll find these indicators not in outcrop, but in concentrated trap zones, stream sediments, gullies, or colluvial fans. The most efficient method for isolating them is through wet sieving and panning. Use a 20 or 40 mesh sieve to remove lighter overburden, then concentrate the heavies. A batte or deep cone pan helps trap the densest grains at the base. After drying, sort under a hand lens or microscope. Once isolated, arrange grains by magnetism with a small rare earth magnet, luster, and color. This sorting helps you identify mixed assemblages, common in areas with both ultramafic and metamorphic inputs. If multiple indicator grains appear together, especially in a terrain with no exposed source rock. It may suggest a buried intrusive or pipe. However, caution is essential. Zircon is a frequent false positive. It's heavy, resilient, and often reddish-brown or orange. While zircon can indicate granite pegmatites or sedimentary provenance, it does not point toward diamond or ultramafic systems. Similarly, almandine garnet, common in metamorphic schists, is not diagnostic on its own. Without composition checks, like Mg/Ca ratios, it's easy to misread the signal. To resolve this, advanced field setups may include portable XRF for T/CR readings, but even without high-tech gear, careful sampling grids and repeatable trap site collections can triangulate the likely source direction. Record GPS points, sediment character, grain counts per pan, and changes across gradients. The convergence of garnet, chromite, and ilmenite grains in stream traps is rarely accidental. It speaks to proximity, usually within a few kilometers, of a primary source. But that source may be hidden under later sediments or have no surface exposure at all. The next challenge is understanding how later events, heat, fluids, tectonics, may have altered or overprinted those primary signals. When the mineral suite shifts in unexpected ways, it often means you're entering a second, more complex phase of the system. Just when the indicator minerals seem to converge, garnet, ilmenite, chromite all stacking in stream traps across a focused area, the mineral signature began to change. Grains became altered, colors dulled, and previously dense concentrates thinned out. At first glance, it appeared the trail had gone cold. But what unfolded was more instructive. A textbook case of hydrothermal overprint, the secondary mineralization process that reshapes, masks, or even replaces earlier clues with a new, layered signal. Hydrothermal overprint occurs when later waves of fluid movement, often from deeper or regionally reactivated systems, alter the existing mineral fabric. These fluids, rich in silica, carbonate, and volatiles like sulfur and chlorine, can enter through reactivated faults or fracture zones, modifying the chemistry and texture of the original deposit. In field terms, this means previous indicators might be partially replaced, dissolved, or recrystallized, obscuring their origin. The first clue was a shift in garnet color. Instead of deep red or purple pyrope grains, newer samples turned orange-brown, often fractured or rimmed by soft, chalky alteration. Under the loupe, they showed pits and weathering not seen in upstream samples. Chromite, too, became less dense, its luster dulled by surface coatings of limonite or manganese oxides. These changes pointed to surface exposure and chemical attack, especially from mildly acidic or oxidizing fluids. In outcrop, the host rock confirmed the overprint. Originally ultramafic terrain had been crosscut by carbonate veins, silicified fractures, and patchy sericite halos. The quartz veins were no longer sharp-edged. They had been partially reabsorbed, bleached, or recrystallized. Faint iron staining trailed down fracture planes, not from pyrite weathering alone, but from sulfide dissolution, evidence of a fluid event that carried metals, but didn't necessarily deposit them in the same configuration. Such overprint is not a setback, it's a clue to vertical system complexity. It means that the primary mineral system, possibly diamondiferous or gold-rich, was later modified, perhaps enriched, perhaps diluted. But it also means that second-generation deposits could exist in overprinted zones, often at structurally favorable sites like dilation jogs, breccia pipes, or pull-apart basins. In some of the richest camps globally, this overprint phase introduced new gold into earlier barren structures. One field indicator of hydrothermal overprint is clay alteration. Smectite, illite, and kaolinite may coat fractures or occur in soft, chalky seams alongside harder quartz. In some cases, these clays fluoresce under UV or show distinct XRF signatures, high Al or K values, suggesting they replaced feldspar or mica. Even more telling are boxwork textures, voids in rock left behind after sulfides dissolved, their outlines still preserved in limonite or goethite. These overprinted zones often carry fine-grained disseminated gold, too small to see and too scattered to detect in pan tests. But crushed samples, when run through cyanide leach or fire assay, often reveal surprising grades. The challenge is knowing where to sample: the altered selvages, the brecciated margins, or the zones of strongest silica flooding. Mapping overprint involves recording not just mineral changes but structural overlays. Are new veins cross-cutting the old? Is there a temperature gradient preserved in clay assemblages? Are magnetic responses muted, indicating magnetite destruction? All of these point to overprint zones, and if alteration is zoned laterally or vertically, it suggests an organized, possibly economic second system. Yet this layering also increases ambiguity. The overprint may obscure pathfinders, skew field readings, or lead to misinterpretation of age and source. That's why structure becomes critical once more. To make sense of altered indicators, you must map fracture mechanics, the way rocks cracked, shifted, and opened under stress, to isolate where fluids moved, pooled, and precipitated. Understanding this geometry is the next and most spatially predictive layer of the hunt. When the clues blur, when alteration overprints and mineral indicators degrade, the clearest guidance often comes not from chemistry, but from geometry. Fracture systems, and how they interact with rock types, control where fluids moved and where they stalled. In essence, the ability to predict hidden gold or gem deposits depends as much on reading mechanical pathways as it does on recognizing mineral signatures. Fractures don't form randomly. They respond to stress regimes, regional compression, extension, or torsion, and they do so in consistent patterns. Understanding this allows you to target ore chutes or vein pockets with surgical accuracy. The most valuable zones tend to occur at intersections, bends, or offsets in these systems, places where fluid flow slows just enough for minerals to precipitate. One key pattern is the dilational jog. Imagine a fault that bends slightly or steps over, creating a small void under tension. These jogs act as traps for hydrothermal fluids. When fluid enters, pressure drops and gold or silica precipitate. These jogs often appear as quartz breccia zones or stockwork, veining with irregular textures and multi-phase mineralization. In practice, they may appear as a zone where vein frequency increases rapidly or quartz becomes ribboned and broken. Mapping fracture density helps too. In competent host rocks like granite, fractures tend to be wide, brittle, and clean, ideal for large quartz veins. In schistose or foliated rocks, fractures may be more diffuse or parallel to foliation, producing vein swarms or layer parallel mineralization. Where the two rock types meet, a mechanical contrast zone, veins often widen and mineral content increases. Another hotspot is the apex of an anticlinal fold, where bedding curves upward and extensional fractures form at the hinge. Fluids rising from depth follow these fracture networks and pool near the crest, especially if a competent cap rock above slows their ascent. These zones, though hard to expose at surface, often leave subtle clues: folded bedding in float, bent quartz stringers, or asymmetric cleavage in wall rock. To triangulate these pockets, fieldworkers often employ a grid system, establishing regular sampling lines across a suspected structural zone. Rock chip sampling at 5–10-meter intervals, coupled with portable XRF readings, allows detection of geochemical halos around the chute. In complex terrain, trenching across lineaments or VLF, very low frequency, geophysical surveys can map conductive breaks hidden beneath cover. But geometry alone isn't enough. It's the combination of structure plus signal, fractures that not only channeled fluid, but also intersected receptive host rock and formed long enough to allow deposition. For instance, a sheared contact between serpentinite and slate may create abundant fractures, but if fluid chemistry was incompatible, it may have healed without leaving metal behind. Timing matters too. A fracture formed after mineralization becomes a clean break, barren. One formed during or just before mineral deposition is mineralized. In the field, this shows up as vein material that matches wall rock deformation, folded, sheared, or recrystallized together. In contrast, post-mineral veins often appear straight, unbroken, and displacing earlier textures. One field trick is to check whether vein quartz shows drag folding, boudinage, or ribbon textures. These features imply deformation during or after mineralization, a sign that the system remained open long enough to matter. Conversely, veins with sharp, undeformed contacts may be later stage or barren. Ultimately, fracture mapping provides the spatial logic that mineral clues can't. It tells you where fluids moved, where they slowed, and where repeated openings may have created high-grade zones. Once these zones are located, the next question is scale. When do you move from hand samples to full trenching or grid drilling? The answer lies in economic thresholds. How much signal, over what area, justifies real investment?